All right, it is time for us to get started. How's everyone doing this morning? Alive, doing okay. Enough caffeine there for at least part of the morning. So the first thing I wanted to do at the start of today's class was correct a mistake that I made at the end of last class. And Michael came to my office and helped me figure that out. So it's not here, but thanks to him for that process. So at the end of last class, we were talking about simple grammars, and I was talking about the reason why the second one is not a simple grammar. And the answer is not because there are two productions that have capital S, capital S. It's because there are two separate productions that lead to the terminal A. Okay. That have different sets of non-terminals associated with them. So that's what creates the issue here. Is it's the two separate productions that have this lowercase a in it with different non-terminals. Which means there's a branch of the different numbers. There are multiple ways that we could continue if we see an A. The entire reason this terminal comes first, and we'll get to this later, is that it helps us parse the current character that we are looking at. And if there are two different ways to do that, that creates a branch at that point. And we could either apply this production or this production. And when we're talking about determinism, that's not good. We can't have an or associated with that. So simple grammars are mostly used for deterministic languages and deterministic push-down automata that we will talk about soon. Probably tomorrow. Maybe not. Eventually. In the next week or so. But I did want to make sure that that was clear as to why this is the reason this is not a simple grammar. We have two different productions that read in a lowercase a, and the productions are different. All right, the actual first topic of the day is going to be a deeper dive into ambiguous grammars and being able to identify ambiguous grammars and what we can do about ambiguous grammars. So we'll start with the definition. We just need an example string in the language that the grammar can produce that has multiple possible parse trees that can be generated to produce that string. So maybe there's some string. Here's the grammar. This is the same sentence I think we've seen before, AABB. No, it's not. This is different. So AABB can be produced with multiple different parse trees from this grammar. Take a couple minutes, see if you can draw out a couple parse trees here that determine AABB, or they reveal AABB over the course of those production applications, and determine whether or not this grammar is ambiguous. The wording here says that it is. See if you can show it. Do you remember drawing parse trees? A long time ago, what, yesterday? Yeah, that was a long time ago. That was another Monday. It's been a whole week between yesterday, Monday, and today, Monday.
Say good and compliment. It's so much. Yeah. I'm not sure. Well, I can tell. So like,
All right, if people managed to come up with a couple of parse trees for this.
there's something very because I feel like.
So just for constructing AABB.
Yeah.
There should at least be. I don't know if there are more than two.
Well, can't you just turn the first S into any amount of S's and then turn all of them?
Turn all of them into lambdas. Yeah, I guess you could do that. Yes. Without the lambda. Yeah, there'd only be a couple, but yeah, no, you can have an arbitrary number of S's and turn them into an arbitrary number of lambdas. So here's one parse tree that reasonably makes sense. You just repeatedly apply the first rule. And here's another. You can see that the first parse tree is kind of a subset of a subtree of the second one, and you could, yeah, apply an arbitrary number of those S's before you decide, all right, one of these S's is going to become the following tree. So, yeah. English frequently has ambiguity in its natural language. This is acceptable to us for some reason that I can't quite understand. But in programming languages, ambiguity is a terrible thing. And it's a terrible thing at the compiler level. Can anyone think intuitively why that ambiguity might be a bad thing if you have a compiler trying to turn a higher level language into a lower level language?
Well, I think the programmer would have one idea of what the code is going to do, and then the compiler would take it differently, right? If it was kind of like some ambiguous meaning, like it could go like either way.
It's more so that it's ambiguous how that translation happens rather than the result of that translation. But the programmer absolutely wants to know, or the compiler needs to have the same way of approaching it. If the programmer programs something and the compiler has a choice for how it can handle that, then do you know the efficiency of your code? Do you know exactly what? And yeah, I can produce some not well-formed. It just creates a massive headache at the compiler level. And then some of that comes through to the programmer's level, where the programmer has to think about what compiler am I going to use for this? Because the different compilers are going to work very differently. So ambiguous grammars can frequently, not always, but frequently be rewritten to remove the ambiguity. So we're going to talk about how we can, what tools we can use to remove ambiguity from grammars and identifying that ambiguity in the first place. So a really good one for this is taking a grammar for simple math expressions. I've seen this multiple times in courses like this being used to explain this, so I think that it's reasonable. Basically, we're going to make a grammar to represent parentheses, addition, and multiplication. That's all we really care about, but we need to be able to express some kind of expression that has an arbitrary number of additions, multiplications, and parentheses. And then, of course, we just restrict variables to A, B, and C because simplicity. Obviously, in a programming language, you have variables that need to adhere to certain variable forming rules, But there are an infinite number of viable legal variable names that you can choose. Take a look at the grammar. And then try to answer the question, what is the order of operations? This grammar may or may not adhere to the order of operations that you expect from math. Looking at its form, how do you know? Guesses?
I mean, when you're like constructing it, you always have to make the parentheses before you put anything in them. So I would assume that like would happen first.
Do you though? Do you need the parentheses? You need them around subcomponents, but you could expand E into E times E times E times E times E times E times E and put parentheses around an arbitrary number or something.
What do you mean by the order of operations then?
So, yeah, parentheses would be evaluated first, but only if the grammar forces that, right? Otherwise, you just have a list of symbols. So could you perform a sequence of derivations that would do addition before multiplication? Could you do a sequence of derivations that would do multiplication before addition?
It seems like it's just the order that you put them in.
Yes, that's exactly right. So there are no order of operations in this grammar. And basically, it just matters if we're going to read them from left to right and do the order, the operation that is listed there. So this grammar is ambiguous, and one way to envision ambiguous grammars is it's very much like a mathematical expression where we don't have order of operations. So how do you resolve this? There's no rule that specifies the order, so it just happens to be whatever comes first. That's a great way to put it. So how would we evaluate the string A plus B times C? Well, we do A plus B, and then we would multiply it by C. And to be able to see this, we can draw a parse tree. So here's exactly what this would look like. I actually misled you. This would not be A plus B times C. This would be B times C plus A. How do you know? We actually have to look at this recursively, because this definition for E will not be resolved until we understand the value of this subexpression. When we start to parse this is unknown, so we need to expand out to get the B and the C and the times to be able to resolve this so that we can do this. So it's worth thinking about the parse tree to figure this out, because this parse tree could be constructed. But this parse tree can also be constructed. Right? This is also a legal way to produce A plus B times C if we're doing a depth first search through this. So nothing about this structure tells us anything about the order of operations. If we do a leftmost derivation, we get this. If we do a rightmost derivation, we get this. And depending on the leftmost versus rightmost derivations, we have a completely different way of understanding this expression. That's not good. That means we'd have to use a leftmost derivation and or a rightmost derivation depending on the form of the expression to try to get it to work with order of operations, which would mean that there are really complicated rules rather than just reading the grammar, which is really bad. That makes compiler construction super difficult, and it introduces a lot of possibilities for error. The logic behind it is really complex. So this would be much better if we did not have an ambiguous grammar. If we had a grammar that always adhered to a particular order of operations. Multiplication happens before addition, regardless of where it shows up in the expression. So, do I want to go straight into this? I actually kind of want to make this an exercise. I don't know if people are going to be able to do this, but I think it's worth just exploring this idea in advance of what would you do to this grammar? How could you modify this grammar to make sure that multiplication always happens before addition, regardless of if we do a leftmost derivation or a rightmost derivation?
Have kind of like nested productions where like use more variables of like e goes I to
Yes,
e.
I think the big issue here is we have one non-terminal going to all of these possible productions. That's a big problem if we're trying to force a particular order of operations. So play around with this a little bit. See if you can introduce some other non-terminals and see if you can force multiplication to happen before addition. And I think this would be, since this one's pretty difficult to see offhand, do this in small groups. Find maybe about 4 people total. And see if you can talk this out and come up with a solution, or at least get close to a solution, even if it's not perfect. Just think through the process and see if you can come up with an answer. That actually, I've done it with that too. It's very possible to put exponentials in there as well. It's another layer of the same kind of complexity.
Sure. Multiple. So.
That's not tech.
X. On the left side. Main one. The only one you can make right side does have to do X times. But like, what is it? Multiplication is exclusively on the side. When you transform, you can only add more multiplication. And then, you know, vice versa on the other side. I mean, yeah. Like, so that all. The always has to be all multiplication. That's why variables and stuff, but I like that's a pretty straightforward approach without, having to manage, you know, the sequence level. That's like your hard setting that. I kind of.
So what was the solution you guys said? So thinking about that, like X on the left side. And Y on the right side does activate those exactly, but make it where like, I mean, this one goes, doesn't matter. But on the left side, it can only get transformed into multiplication. And on the other side, it can only get transformed to addition. Right? I don't know what X and Y is.
My only thing is actually, so there's, he's implying in a sense, where like X is strictly multiplication, so you only do multiplication on the left hand side of the graph. And then on the right hand side, you can only do strictly do addition. And so at the end, when it combines together, I see we're putting it.
Can we only do right hand side operations?
I don't, so what we're proposing is. If it's a left side grammar. That it gets resolved left.
Okay.
We're just gonna cram all the multiplication, we're forcing someone. Multiplication up front.
Okay.
And then you can only do addition once you're completed.
Yeah.
With the multiplication.
Um,
So hard sets, it's not the most elegant thing, because you can't switch the order, but at least they're forced into.
what if you try to do? What would you? Does someone try to do like multiplication, addition, and then multiplication?
Yeah, we're not allowing it. But I see, like, that's what I'm saying. This we're just like orders.
But I think there would be formulas you couldn't do.
Is I guess what I'm getting at. Formulas like. With, like, you wouldn't be able to rephrase a multiplication, addition, multiplication thing as just multiplication, then addition. Like, there's like addition. Of a multiplication sandwich, you know what I mean? I'm not sure if there's a way to like if that's fine.
It still might actually work out if you also do. I don't know, like what our restrictions are, could be something we do multiplication left hand, right hand addition. And then you can kind of like build upon it, and then like now it's kind of like. Well, you can add and do multiplication later, but it's still that's resolved in such a way, like the person who's like language being done has to be like. The user has to be. Conscious, like, there is a sequence in here that works out something above, but realize. Yeah, you have to be aware of the process of sequencing, so now it's on the
I know.
person who's
That's
sequencing this out.
That's, oh. Goodness.
And it would allow for someone like, hey, I don't really like to do. I don't want to do addition or.
No, actually, yeah.
Cause like. You could skip if you wanted to just say, hey, I just want to do the multiplication before I go to an addition. And so you can, the inputs could just be like, oh, we're just gonna put a 1 or a 0 or something. If it's multiplication, you put a 1, so nothing happens. If it's addition, you add 0, nothing will happen. And so that can also be something where like, it's on the user to sequence it correctly, but they can build upon.
Okay.
So one way is like, we do a lot of times where you add there's something already built, like the XY thing, so there's like X, S, Y. So just putting stuff in, and then we'll have another way of like being able to have like X, Y. Yeah, you'd have to have a way where you do X, Y after the statement or something like that. You can build it that way. And so it's only like S's on the, you only have to allow S's in the middle of the X, Y, or at the end of the X, Y, and then you can build it that way.
Okay.
I like.
I think I'm like kind of, I guess I get the juice.
Yeah, so X, S, Y. Or
Side. What if we? Finally, should just some ways we put it. Or parentheses.
Honestly, that was my first like, couldn't you literally just put parentheses around everything and force it to be its own?
That's also true.
Yeah.
Also, I think
But that would also, God, that was so many. Disgusting.
If you, I love parentheses. I don't give a shit about parentheses or anything. I'm like, I love how strict a parentheses is. It's like, no, there's no ambiguity.
As long as it's every
They're not.
They are so annoying to draw. They're like the bane of my existence. Cause
Mine
what was
was
that
like
one?
weird threes.
I just do like, I just give up and squiggle. I just do a vague squiggle. What was that one class where like you had sets?
It's literally.
Was it? Yeah, it was like a section, it was like, you have sets, of sets and sets, and then you end up with like,
I know.
you have a statement, which is just almost like part of the it's gross.
My superpower is managing my ADHD, and so the reason why I love parentheses and curly braces and why I draw them well is because it left ambiguity. If I was able to do that correctly, I'm less likely to get the problem. So it's very, I paid attention a lot to how I did this, so I didn't mess up those.
I hate that symbol.
I just make them look like.
Okay.
weird trees. And then if they're tall enough, then they're just. Other numbers.
I personally have solutions and have not like figured out a way to make it.
I hate that.
All of this from those, I think just do I think most of
So
like, I am so late.
That's the same as your parentheses, bro. I see your.
No,
parentheses. No, not parentheses, your curly braces. I see your
No,
curly.
that is my curly brace.
And it's your summation sign.
No, my summation is nice.
How do you break out?
My summation is fine. But for curly braces.
Like, say you just said
I cannot be bothered.
You would use it.
Alright.
I was just testing it out. Not thinking. I'm not sure. But then we also have to do like. I don't. Lambda, I don't know how John.
Lambda is like an upside down lowercase one.
I also have like the same. Right, it's backwards. Yeah. No, but like, one thing, what directives?
Yes, I think that was.
No,
Oh,
I get that, right?
Oh,
We don't have
yes,
to
they do.
start out of the- No, that's.
I mean, I'll forget it.
Wait, you can replace it, no.
You just need to play more Half-Life and it'll get burned into.
Yeah, that's true.
I think we'll. Yeah. You could add it, or I don't think that would screw that up. But I also don't know if that kind of ruins all that.
Because I keep wanting to do.
That's correct. That's correct. Wait, no, that's not correct. That's. That's my key.
That's not bad.
You want like that? I used to write.
I can see this doing it.
Like.
Maybe I should do that.
Like accidental or like.
Accident. Because I read that as for. Yeah. Because I just forgot how place used to go.
I am, except I have that really weird thing when I'm writing also and use the letter R into the number.
I promise how do I count?
Sometimes. Where
I think I know exactly.
I don't.
Also like P and three.
Anytime there's like strings, and there's a bar or a fire, it's like a fake empty shot that I like swallow.
Oh, change everything from
So, you know. Explosives like words so high. Everyone's like, I was lost. First letter. That kind of is solving his drama. But she's always just trying not to. Yeah. I was just trying to think of random letters.
Is that a translate?
There's no.
So.
Well,
Because terminal. So this. This is non-terminal because it does not.
So I'll give people a hint at this point, because I think that might be useful. I hear really good discussions going on. But I think the prior parse trees on a couple slides ago help a lot with this process. Recognizing that in order to be able to evaluate the initial expressions, we need to know what each of those evaluate to. Which means we have kind of a depth first search or recursive approach to this whole process. So what should the start symbol eventually resolve to first? What do we want to be tackling first in the order of operations, starting from the start symbol, so starting from the top of the tree? What's the first type of expression that we should be looking at? I would argue that's probably the last one we want to look at. Addition. Yes, we want to start at the low precedence levels. because we need to figure out what the left-hand side of that addition is and what the right-hand side of that addition is, and they could be made up of complex expressions, but the very last thing we want to do is add them together. So those sub-expressions may be made up of addition, so we need some way to go from addition to addition. We need some way to go from addition to multiplication, and we need some way to go from addition to parentheses. If we have multiplication, we can't have addition inside of that without going through the entire loop back to addition. We can't allow addition as a subpart of addition, but the hint is this is eventually gonna look kind of like a loop, where we can turn an expression into an expression by considering things like, is it addition? Is it multiplication? Is it parentheses? If it's parentheses, then what goes inside of the parentheses could be anything. Maybe I kind of want to go around to each group and talk about what have you been discussing? What are you, where are you? What have you been discussing? What conclusions have you come to? I do not expect an answer. This is a very difficult question, but I think just priming yourselves with thinking about grammars and how that works can help to understand the solution when the solution is presented. But I don't know, does any group want to share their findings or their thought process?
I can throw out my lazy solution.
Yeah.
Potentially.
Yeah.
Could you just put parentheses around like everything, essentially, so that it's always like its own term and there's never ambiguity?
Well, what happens if you want to override the order of operations? So you want to have something like some expression plus some expression, and you want to have parentheses around that whole thing. Because you want to override the order of operations, so you don't necessarily want parentheses inside of that, you want parentheses around the whole thing.
Well, I think if you have the E goes to E in parentheses as well, I think
Yeah.
you could do what you're describing. You would just need to know the order to do it like properly.
Right, you need some way to loop around from parentheses to parentheses so that you can throw parentheses around an expression and then further define what that is going to be.
As I'm kind of building it, I'm running into a lot of like or cases, like S can go to this or, and then like. Am I on the right track there or am I just?
There, in my solution and the book's solution, the only ors are still in the terminals. There are no ors in any production involving a non-terminal that's not turning directly into a terminal.
Oh, there's no builds in this solution?
No ors.
Huh.
Do we want to see the answer? Do we want to have a little bit more time to try to produce something?
I have a bit of a thought process.
Yeah, let's hear it.
I figured if you have like kind of a hierarchy of like. When you're making like one of the operations is kind of terminal, like if you're making multiplication, you can't like put addition in the multiplication as one of the letters. You have to make the addition first and then do the multiplication.
That will work unless you want parentheses to override the order of operations. So we need to be able to loop through parentheses to get back to the top to override the order of operations with parentheses.
My solution doesn't go with parentheses, right?
Yeah.
But if you don't have parentheses, that's multiplication.
Yeah, it's a much easier problem if you don't have parentheses, but the ability to override the order of operations is really important in mathematical expressions. So it's important to include in the grammar, or try to find a grammar that includes it as well.
I just want to ask, how many statements of that?
How many productions?
How many productions is the answer?
7. Well, it's 6 plus the ors that produce terminals. So
Okay.
6
That's what
non.
makes sense. So I feel okay.
Let's take a look at the answer. Here we go. So this is actually quite interesting. We have an expression E that can go to whatever T happens to represent. T can go to F, F can go to I, and I is one of your terminals. An expression can be made up of addition, only addition, but it can also go directly to be a T. But the left-hand side of that addition can stay as an E, but the right-hand side needs to be forced to be a T. Once we have that, we can define the T to be a multiplication. And F can have parentheses around it, And that loops back around to the top, and any expression could be inside of that parentheses, because the parentheses completely overrides the order of operations. So anything can be inside those parentheses.
So close.
That's really cool. That's really cool that you were that close.
Why don't you have ors? Why wouldn't you just have T as F or T times F? Is that just,
If you do ors like that, I mean, yes, you could, but then you can't force. I think it might be a little bit clearer
I'm
if
just asking if
we.
it's logically equivalent if you have ors. Or should the second?
I
be-
don't think it is, because only Fs can have parentheses around it, and Ts can be themselves multiplication, so that's what allows you to have like A times B times C.
Yeah, I guess I was just
Without-
asking because there's
I
three,
think it might be, actually, it might be equivalent, because this forces everything to be of 2, and then you need to loop in order to get 3, and I think with yours, then you might just be able to do it with a single production.
because there's 2 productions with, that's like E leads to something, so I figured it would be logically equivalent to just, instead of having 2 productions that are E, there's
Yeah.
one with an or.
Yeah, you could do that.
Works that way.
Yeah. Well, I don't know, I think reading it this way, like putting it that way is a little easier to follow, but it would
Right.
just be.
Yeah, but you only need. I guess if you have an or, they're still technically separate productions. So it would still be 6 productions, but you only need that number of variables. But you can see now exactly how that order of operations happens, even though. We're kind of forcing the plus to be at the top here. We're forcing the plus to be the thing that is highest up in the tree, and then multiplication to be the thing that is next in the tree. And then parentheses would be the next thing, and then below that, we could have anything. The parentheses kind of resets that. To be able to have any sub-expression under that, but that sub-expression would be defined to be pluses before multiplication, before parentheses, etc. So that when you parse it from the bottom up. Recursively, you would be doing the appropriate order of operations. You'd be doing parentheses first, followed by multiplication, followed by addition. And that leads you to that appropriate order of operations that we're searching for, hunting for. So do not feel bad if you did not come up with this or something close to this. This is, until you've seen it and have practice with it, it doesn't really make sense. So you're not gonna generate it on your own. But hopefully by seeing it, that at least makes some logical sense with the order of operations, with bottom-up parsing. With recursive tree-based, like mapping it to tree algorithms. And seeing the link between the stuff that you've done in data structures or algorithms. Paired with this. Hopefully helps you see why this grammar is correct. Does anyone have questions? Yeah,
So ours is a bit of that, except where it had, you have E going to E plus T, and then you have E going to E plus E. And then since E can go to T, we didn't change anything there.
right.
Would that work, or why would that?
I'm thinking that's probably okay, because there's no other thing that the E can go to. But it does kind of force the. It forces you to do. Right side first, not necessarily. I'd have to play around with it to really be able to see. It's complex enough for me that if someone presents me with an alternative that is close to the same thing, I actually have to go through the logic myself.
Because yeah, we had the exact same thing, except we had where it has E going to E plus T, and E going to E plus T, and T going to T times. Everything else was the same, and with the exception of we didn't have that function, we just had another F that said F can go to parentheses, E parentheses, F can go to A or B or C.
Yeah,
Cut out that last I part right there.
Yeah.
Other than
I
that-
think that might be okay. I'd have to draw that out on a board to really. come up with a complex expression, come up with the parse trees for each and see if the differences there actually matter in the end. But my intuition says that it might not matter. That's really cool that you came up with that, though. Other questions about this?
Kind of a side question, so if you have a range of terminals, say like you have terminals like 0 through 9.
Yeah,
You just put 0-9, is the like I goes to that, or do you have to do I to 0 or 1 or 2 or 3?
if you're being formal, you want the 0 or 1 or 2, because you don't really know what does that range entail. If there's a definition somewhere that says a dash means in the ASCII code for a character, it means everything in between the first character and the second character. You have that kind of definition, then you can start to use that to represent, but you'd have to refer it to some kind of reference that defines what that means formally. So as you can imagine, if I just gave you this grammar and said, is it ambiguous? Without giving you any context for this is the correct way or a correct way to come up with precedents for mathematical expressions. And I asked you if it's ambiguous, you'd have a really hard time saying yes or no to that. There'd be a lot of work that would have to go into that ambiguity. And in fact, it's so much work that no algorithm actually exists that we are aware of that can always answer this. Is a particular grammar ambiguous? There's no process that we can go through that determines whether or not it's ambiguous. You'd have to actually brute force it and say, for every possible string in a language, of which there are infinite, generate parse trees, as many parse trees as you can for a particular grammar, and there may be infinite, so this process may not terminate, and see if you can generate 2 different parse trees for that. If you can, the grammar is ambiguous. That is a tall order. Sometimes there's ambiguity in the language, which means that we cannot build a grammar that does not have ambiguity in it. This is especially rough on us compiler designers. So here's an example. A to the n, b to the n, c to the m, union a to the n, b to the m, c to the m. So first ask yourself, is the language context-free? And to answer this question, we want to look at both sides of the union. We know that if the left-hand side is context-free and the right-hand side is context-free, the entire language is context-free. So looking at the left side of the union, could we build a grammar for the left side of the union? Take a minute or two, see if you can come up with a grammar for the left side of the union. A to the n, b to the n, c to the m. So n is the same, we need the same number of a's and b's, but there needs to be a different number of c's. I guess m could be equal to n. There's nothing that says that m is not, but we allow for a different number of c's than a's and b's, but the number of a's and b's have to be the same. There's no clause here that says that n is different from m. It's not equal to m. So because of that, we can have the same number.
I just, what are we building on the left side?
Grammar.
Okay, thank you.
So it's not quite as hard as the last one, hopefully. We basically first need to produce all the Cs, and then we need to transition to producing pairs of As and Bs.
You said M cannot equal N?
It can,
It can.
because there's nothing in the definition that says that M can't be equal to N, then they can be the same. If they couldn't be the same, that would make this a little bit harder. It's actually easier if they can be the same. Because I want to get through this one slide, I'll have the answer a little bit quicker here. Like I mentioned, we're gonna produce all of the Cs. And then we're gonna transition to producing pairs of As and Bs. So S1 is gonna loop to S sub 1, or this could just be S, depending on how you wanna make this start on terminal. We're gonna loop this process, producing Cs, producing Cs, producing Cs, producing Cs, until we choose A. Once we choose A, we can't get back here and produce more Cs. So we're going to loop here, producing As and Bs, As and Bs, As and Bs, As and Bs, until we're done. So because we can make a grammar for it, this language is context free. Right side of the union, very similar. Now we have B and C being the same and A is different. So we're going to produce and loop A's at the front, A's at the front, A's at the front, A's at the front. Eventually we're going to transition. And at the end of this, we're going to be splitting and putting B's and C's at the end until we're done. So this union is also context free. How do we know that a union is also context free? We can add a fairly simple start that says, all right, well, we start and we can either go to the left side of the union or the right side of the union. Does that make sense? You just choose at the beginning of the grammar which direction you're going. Am I going to produce the left side of the union or am I going to produce the right side of the union? And then the grammar can handle the rest once you make that decision. But note that that decision has to happen immediately. As soon as you read the start symbol, you don't get to wait and count some numbers to decide which one that you're in. You need to decide immediately, am I in the left-hand side of the union or am I in the right-hand side of the union? Does that make sense? So we have a restriction on the left side on the number of A's and B's because they have to be the same, or B's and C's. Meaning that if N is equal to M, there's no way to produce A to the N, B to the N, C to the N. Basically, we have the ability to produce the left-hand side or the right-hand side, but how are we going to handle that? Think of it in terms of if you were trying to model this language at the beginning. Let's say you start seeing some A's. We either, if we're on the left-hand side, need to be pairing them with B's. We need to be counting the A's because we need to be able to know how many B's there are. And on the other hand, it doesn't matter how many A's there are, we need to be counting the B's. And there's no way to do this. If you think about having something like a stack structure, I recognize we're out of time, but you have some kind of stack structure. Do you count the A's or do you ignore the A's? If you count the A's, when you come across B's, do you remove the B's from the stack or remove the A's from the stack to see if you're matching A's to B's? Or do you add B's to the stack because you later need to match them with C's? We don't know what we need to do to be able to count this as we're parsing it. So because of that problem, this particular union has problems associated with it. We're going to talk more about that over the next couple of days. But for now, it's an intriguing problem. See you all tomorrow.
So it would be like. The way of it is something like that, say that, we have. Some people sort of. What do you mean land, like, what symbol on lands? Like, the. Like, some, like. Oh.